Now, there's something that might have been nagging you, which is the fact that we really haven't talked about the sample size a great deal. I mean, we've talked about how it affects the margin of error and therefore the confidence interval, but that's not actually the real issue with sample size, is it? I mean, what if you went out and you went through all this effort to collect data, and most of you now have an idea from just starting to think about phase two that it's a lot of work collecting data. You go out, you collect this data set, you compute a confidence interval, and the margin of error is too wide. You want something that's more precise. What do? Well, you've wasted a lot of time, right? You have to go out, you have to collect more data. It may not be so easy just to combine those two data sets. So, now we have a problem. Or what if, on the other hand, you went out and you collected a really big data set? You said, well, I'm going to be kind of proactive, right, and cautious. I'm going to collect a huge data set, and the margin of error is a lot more precise than what you need. In some sense, that's almost worse because now you've wasted a lot of resources and time collecting data that you didn't need. So what would we really like to do? What we'd really like to do is this. We'd like to start off and we would like to say, okay, if from the beginning I specify the margin of error that I desire and the confidence level, how can I get the sample size that I need? So you're going to tell me how precise you want your estimator is. That's what the margin of error is, and you're going to want it, and you're going to tell me what confidence level you want to use, and I want to come back and I want to tell you what sample size you need to get a confidence interval that has this confidence level and has this level of precision or this margin of error. Okay? And so where I'm going to, and so this is kind of the idea, right? We want to know when it's large enough, but we don't want it to be too large, and we want to be able to compute the sample size um, for any desired level of precision for any MOE. Now, how do we do this? Well, let's just start off with some of the basics, right? So let's look at a confidence interval for pi. And let's look at the expression for the margin of error. So the margin of error is equal to our z-score. And I'm not going to bother writing 1 plus confidence level divided by 2. Everyone knows what the z-score is here. And it's pi hat times 1 minus pi hat divided by n square root of. And so now think about what we're given here, right? We're given the margin of error, and we're given the confidence level, which tells us the z-score, right? So these are two things that we're going to be given here. So these are things that we're going to be given. You're going to tell me how precise you want the estimator, and you're going to tell me what confidence level. And as soon as you do, remember from the Excel, we use the confidence level to compute the z-score, and I want n. So let's do a little bit of algebra. Okay, I'm just going to do some real quick algebra here. So I'm going to go ahead, I'm going to divide the margin of error by the z-score. And I'm going to square both sides to get rid of the square root. And I'm going to we could cross multiply here, okay? If you wanted to, we can go ahead and cross multiply. So I'm going to have n times the margin of error squared is equal to the z-score squared times pi hat times 1 minus pi hat. And now I can just divide both sides by the margin of error squared. And this will tell me my sample size. Now I have a small problem. Here's my problem. I know the z-score from the confidence level, and I know the margin of error because you've told me how precise you want the estimator, but I don't know pi hat. Remember, the sample size calculation we're doing before we ever collect the sample. So what should I use for pi hat? Well, what I'm going to do is I'm going to be conservative. And I'm going to use the fact that when I use pi hat as 50%, this has the largest value that this can have. So when I let pi hat be 50%, this quantity here has its maximum value. So this will give me the maximum sample size, and it will guarantee it will work for any pi hat. So I'm going to plug pi hat equal to 50% in. And what I'm going to get is n is equal to z times 50 divided by the margin of error squared, where the margin of error is being expressed in terms of percentage, right? So here I'm writing the margin of error as a percentage. And this is a sample size calculation. So this tells me what sample I need, or what sample size I need if I'm doing a population, if I'm doing a population percentage confidence interval. Okay. And let me see really quick if I have this. Yeah. So if I want to go back here now, I can set this up. I can do a sample size calculation. Okay. I have to go to population proportion first, okay? And if you want to copy this down, you can. Okay. And I'm going to do the MOE in percentages. I'm going to change that. So let's suppose, for example, we wanted to do a national poll. Let's just do a sample calculation. So here is an example. Suppose I want to compute what sample size do I need to get a 95% confidence interval. Come on. So let's ask the following question. We'll ask the question, what sample size do I need to get a margin of error of 2% for a 95% confidence interval? This is what they use essentially in political polls, okay? So my MOE is 2%. I need the z-score for a confidence level of 95%. When you do that calculation, and we can do this, it's 1.96, but we'll go ahead and do it here. So my confidence level is 0.95. And it's the same calculation that we did here. Okay. So I could actually just cut and paste right here. And all I have to do is change the confidence level I used before to this confidence level here. And it'll be about 1.96, okay? So that's my z-score. And I just plug it into this. That's all I have to do. So n is equal to 1.96 times 50 over 2 squared. And notice 1.96 times 50 is roughly 2 times 50. So this is roughly 100 divided by 2 squared. And that's 50 squared, which is 2,500. So this tells you that in the political polls, if they wanted to be sure to get a sample size that would give us a 2% margin of error, they need a sample size of 2,500. Now in reality, they actually use a little bit less. Usually it's on the order of like 1,500. And the reason why is they don't do simple random samples. They actually do a type of stratified sampling that's more efficient. But for our case, this is what we would use. Okay, great. So now we know how to do a calculation. And let's go ahead. We'll just complete it here, right? So our margin of error was 2%. So now we would just put this all together. It's equal to the z-score times 50 divided by the margin of error. And it's going to be a little slightly less than 2,500. Okay. If you get a decimal, round up. Okay. So if this was really 2,401.2, I would round this up. And so I'm going to make sure that it's not. No, it wasn't. So it automatically rounded it up. Good. But you want to you want to be careful, okay? And there's actually a way in Excel you can do this. There's actually a command. If you wanted to be super careful, it's called round up. Okay. And then you tell how many digits, and you say 0. That's the number. Oh, because I lost my parentheses there. That's why. Yeah. Okay. And it will automatically round it off. It'll round it up, not round it off. There's a difference, right? Rounding off takes you to the nearest ones place here. Rounding up always takes you to the next higher integer, which is what you want here. Okay, good. Sample size calculation for population mean. Kind of the same sort of deal. We just the expression for the standard deviation is a little bit different, right? But it's the same sort of principle. We start off, we look at our expression here. So if we were doing a confidence interval for mu, we start off now that our margin of error is equal to our z-score times the estimated standard deviation divided by the square root of n. And when you solve for n, you go through all the fancy algebra and whatnot. You get the z-score times the estimated standard deviation divided by the margin of error squared. Again, there's a problem. We don't generally know the estimated standard deviation. So one of the ways we can do this is we can estimate. We can kind of give an estimate of what this should be, okay? Since we don't have the sample yet. We can use this rule that says the standard deviation is generally the range divided by 6. Now, when you think about it, where does this rule come from? It basically comes from the empirical rule, right? 6 standard deviations, a window of 6 standard deviations for a nice symmetric distribution contains 99.7% of the data values, which is roughly the range. So if we can estimate the range, divide it by 6, we can estimate the sample standard deviation. And how we estimate the range, so this can be a little tricky, but basically we're going to use values that are reasonable, okay? We're not going to try to get too precise. And I want to go ahead and work through some examples to kind of show you, okay? So let's work a few sample problems. So going back to the rat empathy study we did, we noticed that we couldn't actually compute a confidence interval because our sample size was too small, right? So remember that for the confidence interval, the central limit theorem calculations are different. Here we have to have pi hat greater than or equal to 10 and n minus pi hat greater than or equal, I'm sorry, um, n times pi hat greater than or equal to 10, and n times 1 minus pi hat greater than or equal to 10. Okay, and we didn't have that with the rad empathy, right? So let's figure out what we would have needed for a decent sample size. So suppose we wanted to get a 95% confidence interval for the population percentage of rats that would open the door, and we wanted a margin of error of 5%. What sample size would we need? So we know with our formula, it would be 50 times z divided by the margin of error squared. And we just saw for a 95% confidence interval, z was about 1.96, okay? And our margin of error is given as 5%. And so notice that this is kind of almost like when we're doing a 95% confidence interval, this number is almost 100. So 100 divided by 5 is 20. 20 squared is 400. A lot different than what we had, right? But let's go ahead and do the exact calculation, all right? So it's 5%. This didn't change, right? So our z-score didn't change. And sure enough, you can see it's close to 400. It's about 385. And again, this is rounded up. Okay. So this next problem is kind of fun. Suppose you wanted to get a 90% confidence interval for the average height of all Embry-Riddle students that had a margin of error of 1 inch. How large a sample size would you need? Well, here we're given that our confidence level is 90%, and our margin of error is 1 inch. And we need to estimate sigma. So it's going to be the range divided by 6. Well, what is the range of heights that you'd expect Embry-Riddle students to have? Well, I don't know. It's just kind of like, give a reasonable choice, right? Right? Maybe 6 feet 6 inches to maybe, I don't know. We'll say, I don't know, 4 feet 11 inches. Seems pretty reasonable, right? So here we'd have what? We'd have a total of 17 inches for the range. And we'll make it 18 just to kind of make it easy here, okay? So we'll make the range. Maybe we'll make this like 6 feet 6.5 inches and 4 feet 10.5 inches, right? So we'll make the range 18 inches. So we plug this into here. 18 divided by 6 is about 3. Notice you have to kind of estimate a little bit, right? And now I can go ahead, I can compute this. So I could have a template now. And again, you might want to stop the video and kind of copy this down on your own, okay? So my desired margin of error was, it was 1 inch, so my MOE was 90. And here I'm going to use here I do have to actually use the decimal form. Okay, my desired confidence level is I'm sorry, this is 1 inch up here. Sorry, never mind. This is irrelevant. This statement right here. I don't have to worry about margin of error because margin of error is a physical measurement. It's not a percentage. So I wanted a margin of error of 1 inch, 90% confidence interval. So I know what my z-score is going to be, right? Norm.s.inv 1 plus the confidence level divided by 2. And this number, you remember it after all, it's 1.645. Okay. And we said our standard deviation was roughly about 3. That actually turns out to be a pretty good, it's a little bit larger than what it is generally for people. And now I go ahead and I plug it into my formula, right? So my formula says here it's going to be z times the standard deviation divided by the margin of error squared. So this is going to be my z-score times my standard deviation divided by, of course, 1 doesn't do anything, but still you have to put it in there because it might not be 1, right? And we find we get 24.3. Okay. Oh, I'm sorry. This is no, that's correct. That's correct. Yeah, yeah. So this turned out to be a really really small sample size. We don't need a particularly large sample size there. Okay, good. All right. And these are just repeats for some reason. Okay. So that gives you an idea of how to do the sample size calculation. And if I ask you what the sample size for a quantitative variable like the population mean is, I'm going to kind of give you an estimate of the range so you don't have to guess, because that part can throw you a little bit off.